computer. Okay. I'm recording. Look at that. Okay, cool. So we need to get here. You're here. And is Gustavo coming? Okay, 17 minutes late. That's about right. Okay, let's get started. So where were we last time? I'll kind of read. So this was kind of the last thing we did, this fake socket thing, and he's here?
Gustavo is here, yeah, he messaged.
Hi guys, I'm here, yes.
Oh, okay, sorry, I just have like, I didn't see you.
No problem.
Okay, I'm scared of everything. So yeah, so at a high level, we figured out how to, let's see, we figured out how to basically do this, right? We could connect with this is the fake socket thing, but we could connect with a real socket. That's the first thing we did, and then we learned how to read bytes, n bytes at a time, you know, for some integer n. And we learned that you could. It seemed like you could kind of take the message apart and understand what it means, and so we did it here, and we also, you know, we found a, you know, a nice way of doing it as opposed to this ugly way up here. We found a nice way of doing it where we could just read n bytes at a time, and then we could read the length of the message, and then we did this smart thing where we would only read that much at the end, right? And then so we would avoid that problem where sometimes we'd read two messages when we were just reading, you know, some fixed number of bytes to try to get the message. You know, at the beginning we were like overshooting, right? We're getting a message that's like 150 bytes, and we're just like, give me 1,000 bytes. And we'd always get a message, but sometimes we'd get two. And so we got a little smarter as we went, and yeah, now I think we're here to the read magic part, to actually detect whether we're on the Bitcoin network or not. So yeah, so let's get started. So we have let's see. So yeah, here's just some stuff. I'm sort of hinting at, you know, how you can look at these different, like the integer and decimal representations of the network magic. If you go to the protocol documentation, they're kind of like backwards. Where are they? They're up a little, I guess. So yeah, you know, like if you look at this one, you know, F9 is on the left or the right, but then it's sent over the wire, F9 is on the left, you know, and then BE. So it's like they're the same, but they're sort of reversed one byte at a time, you know, and that's, I guess at this point we don't really know, you know, we're kind of, it's just like a weird thing that we should kind of take note of, and we'll learn more about why that is later. And so here you know, we can take these numbers, the values. These are just integers, right? And they're a base 16 integer, right? So that's why they have a D in it, right? Because D is what? A is 10, B is 11, C is 12. So D is like a 13. So this decimal place represents a 13 in base 16. It's that, yeah, that's how. It's just an integer, and in Python, it's kind of cool. You can basically enter. Yeah, I guess I get into this. Yeah, so we'll cover this a little bit more here. But in Python, let's just execute this cell. In Python, it's kind of cool. So here's the number 16 or 17, right? And this is just you enter it in as a number, right? And so we print the number 17 is, and then here is. This is what it looks like in binary. And all you got to do is hit binary of n, and This is what it looks like in octal right here. This is what it looks like in hexadecimal. And so we have all these nice little things in Python to convert from integer bases, but and you know, at the bottom you can see that if you take these, so here's the hexadecimal value, right? And we're going to enter it here. Here's the octal here. And so what we're doing here is we're setting up an equivalence. In Python, you can set up like A equals B equals C, and it's just like one big Boolean statement, right? Is everything equal to everything else? And so the interesting thing in Python is that you can enter these different numbers, different bases. If the number's the same, it'll actually evaluate to true. Because under the hood, everything is stored, all integers are stored in just binary. So it doesn't matter how you kind of enter them in. An integer is an integer. And there's no such thing, like within Python itself, there's no such thing as a base 2 integer and a base 8 integer that are different. It's all the same. And then they just give you some of these helper functions that actually, they don't change anything with the integer. They just, they just give you a string. So, you know, so this is the value of hex of n, and the type is a string. It just makes a string representation for it. And so this is, I'm kind of dwelling on this because it's you know, this is one of the things that's kind of confusing about this, you know, getting started in this kind of network programming is like everything's in hexadecimal, everything's in bytes, and everything's an integer. But it's like, this doesn't look like an integer, does it? And this doesn't look like an integer. And it's just not what we're used to seeing when we talk about an integer or a number. And it's one of the confusing things that's gonna be hard to deal with, and that you're gonna learn to do as we kind of wrestle all these bytes that are bits and bytes that are coming over the network. And so if we look up here, you know, just like this kind of, you know, when we saw the hexadecimal, it's just 0x11. 0x is just like a marker when you print it to a string. This is what that I want it to be interpreted as. This is meant to be interpreted as hexadecimal. And when you declare a variable, the 0x is like interpreter, you know, Python interpreter, I'm telling you, this is a base 16 number. And so up here, we can pull these numbers right off the protocol documentation, right? So testnet ends in FA. And so here, oh yeah, so testnet has a long history. We're apparently on the third one, because every once in a while testnet becomes actually worth real coins and they start trading them. So so this should be the value of our testnet. We're on testnet 3, so it'll end in 0B, and here it ends 0B. Okay, good, we have the right value. So these are just hexadecimal numbers, and when you execute the cell, let's do both of them. So, you know, when you print the cell, it's kind of cool. It's just like, this is just an integer. It's just a number. And so this is something, I don't know about you guys, but when I deal with this, it's still kind of weird to be translating bases all the time and, you know, see this, and this is a number, just like the number 1 or 2. So yeah, this integer here is magical. It is what represents a Bitcoin message, right? It's just some crazy, what is that, million? It's 3,652 million, right? It's just a huge, it's a magical number. So yeah, any questions about that sort of, that stuff?
Those two numbers are just base 10, are they? Just normal integers, yeah?
Yeah, well,
okay.
No, so they're actually, so yeah, there's, I really don't know what the right answer to that question is, how to explain it. They're really base 2. Like the way Python stores everything is base 2, because that's the fastest to compute with. This is at least as far as I understand. But when you print it, right? When you print, this is a human they create a human readable version, and so they give you the base 10 representation, And that's what you just come to believe that that's what the number is, but it's actually everything's stored base 2 within Python itself, and within any kind of programming language, as far as I know. And so it's kind of interesting, like, yeah, but I mean, if you really get down to it, there's no, like, an integer is not, it's like, it's the number, like the digits, but it also is the, what base it is. Like, you have to say what base it is, or the number doesn't make sense, right? So it's like, just as this is just an arbitrary representation of this number in some base, so is this, or so is the binary. There's like no right one, so to speak. Does that make any sense?
Yeah, I'm just saying, because there's no like 0x in front of network magic in terms.
Oh yeah, and it's so the point
base 10 is displayed as base 10.
Exactly. Yeah. So sorry. This is base 10, and Python just sort of magically translates this to this. When you print it, it's just interesting to me that it no longer, when you print it, it no longer looks like this. It looks like the same old comfy integer we're used to, right?
Yeah.
Base 10, yeah. So, but you're right. Too long of an explanation. Okay, so any other questions? Sounds like no. So let's go on to actually so what we're going to be doing here now is we're going to create a lot of these little like one-line helper functions, right? Because in our code later on, for example, at the end, we're going to want, we're going to create this message class, right? And it's just going to have 2 attributes, the command and the payload. This is like the contents of the message, and this is what kind of message it is, like version, verac, env. Ivo, you discovered remember when that answer about SegWit you were reading, they're like, okay, you get the transactions, the transaction information is contained in an inv message, right? INV, which is short for inventory. That's this one. But you get this, so this is like one of the message types, one of the command types. But you get an INV message usually you can get it by requesting it with a get data message. Sometimes I guess it's backwards. Like INV will contain a bunch of, like, this is a bunch of stuff you can get all the details for, and then you fill in all the details with get data. So the point is these are 2 of these commands that will, so some of our commands later on will see INV here or get data. And so what we want to be able to do here is we want to have like little helper functions like read length, right? Read command, read socket, read payload. When we create one of these messages, we want these like little helper functions, instead of having to go like, like let's say content length, if we don't do helper functions, it's got to be like int.from bytes of sock.read of what is this for, and then like that's what it would be like raw or something like that. I don't even know if it's right. It's just hard to read. So we want to create these little helper functions to make it simpler. Like, let's just make one that says read length, and then we can read the length out of the message, and then we can test that code, and it's just kind of makes our life simpler. So here's the first one. We're going to do read magic, right? And so all we want to do is we want to read the first 4 bytes, right? Because that's what our protocol document, we're just, we're pretty stupid here. We just do what the protocol documentation tells us, right? The magic is 4 bytes long and it's an integer. So we're stupid. So we're going to read 4 bytes, right? Sock.read of 4. And then we're going to turn it into an integer. And I'm just telling you, this is how you do it in Python. You do int.fromBytes, B, and then little is the byte order. So whether the big bytes are on the left, or the big numbers are on the left or the right of the number. And we'll deal with this a lot. If you don't quite understand this, don't worry. We'll deal with this a lot, and I'll explain it more and more as we go. So that's all you do. You read the bytes, and then you turn the bytes to an integer, right? So this is the type of this is bytes, the type of this is integer, right? Because we want an integer because that's what the protocol documentation tells us. The magic value is an integer. So that's what we're going to do. We're going to turn it into an integer, and then we have these two helper functions, right? Let's check if, you know, let's read from a socket, and let's just say, like, is the first thing a Bitcoin message or not? Is the first thing testnet message or not? So if we execute this, we'll see. Oh, I gotta run everything here. Okay. So if you execute this little cell here, you'll see that this is mainnet message. If we call it on our fake socket, it'll say true. Is testnet message, if we call it on our little fake socket, it's false. And the reason there is because when we created our little fake socket, I used a real network message, right? This is the same, right? F9 is in the front, and if you go down and look at this one here, F9 is in the back because they're reversed. So that's, you know, you can tell this is the example that the kind of example message that I put in this little helper, this little testing function is a real message. So that's why we get that answer. Does that kind of make sense? Any questions there?
I'm good, I think.
Okay, cool. So yeah, okay, so yeah, so we're going to go into a little more detail on bytes to int and hexadecimal. So we already kind of went over this. Yeah, I already kind of covered this. And then, yeah, okay, so here's the endianness. So, yeah, so I still kind of I'm slightly dyslexic, so anything that involves left and right is really confusing to me. So I think big endian is when the bytes are first, so that's left, on the left side of the number, right? So like, you know, the number 1 million, the million place would be on the left, you know, and then little endian would be, I think it's the biggest on the right. I always get, as I said, I'm slightly dyslexic, so it's confusing as hell to me left and right. But it's just one way or the other, and you don't really have to. Yeah, we'll get a little better at this. So let's see. So here we go. If you look at this little link in the Python documentation, it actually goes over this. You know, like here's how you get a big endian number, right? And then here's how you take the same number, right? So yeah, so big endian is the big numbers are on the left, right? So when you interpret this number, it says, okay, these are the small decimal places, right? And so x10 in hexadecimal is like there's 0 in the 16th, you know, 16 or the 1 places, and there's 1 in the 16 places, right? So this is the number of like 16s you have, and so that's why when you interpret it big endian, you get a 16, right? But this one is a little different. This one is now, you know, you gotta flip the order of these kind of in your head, like. So now this is the ones. This byte here is the 16s. This one here is the 16 squared. What the hell is 16 squared? 256, I guess. Yeah, 16 squared is 256, and then the last one here is, you know, 4096. That's what this last. So this is like the biggest byte. It's just weird, right? Usually the biggest number is on the left, and so little endian is kind of like you take the bytes and reverse them. And so you see how you know, when you interpret this byte, which is the same in both cases, in little and big endian, you get very different numbers, right? And so this is the one Satoshi mostly used, but every once in a while he uses this one, which is really annoying. So yeah, so that's kind of how, and there's also, so this is also good. We should discuss this. So there's also signed. So signed is whether it's a positive whether you can have negative numbers or not. So the default is false. And in Bitcoin, I don't think there are any negative numbers, or many. I haven't seen one yet. So signed always stays false for us. And you can verify this in the network documentation. Like every time we see an integer, it's uint32, right? So that means unsigned integer. So it's always positive. There's never any negative integers that are being sent over. And I mean, I think if we look through every version of int32, yeah, so maybe, I don't know, maybe this can be a signed integer. I don't know. That's a good question for our little. So
It
I don't
says
know.
in the comments, this is signed.
Does it?
Yeah.
This is signed. Yeah, I mean, so I guess it's signed in practice, but not in theory, but like kind of not in practice, because like it's a strictly, yeah. So that's a good point. So can.
A version number would never be negative though, so I think it's just laziness, isn't it?
Yeah, well, or just like bad design. Like if you start with yeah, because it's like a strictly incrementing thing, right? You're not going to go. You're not going to go down and. Okay, I can't. Do I get rid of that? Can int 32t. Yeah, because like if there was one little case where it could be negative, of course, our code would really break because there should be a negative number and there isn't. So yeah, that's cool. I just learned something there. I thought every single one of them was unsigned, and so we've got, and so here, look, start height is actually signed as well, which is also weird. Like height is another strictly increasing. Right, like we can't ever, well, I mean, I guess in a hard fork, you go backwards in the height, right? Like when they had that thing with the Berkeley DB, when they had to rewind, you did have to actually go backwards. So the height did decrease. But in general, the start height, this is just where you're at, how many blocks have you downloaded? In a normal operating node, that'll only go up. So, yeah, I guess it won't. I mean, there's probably some cases, but yeah. So look, we learned something there. There are some signed integers in Bitcoin, and I was wrong. So yeah, maybe in the future we'll need this when we read these. Like maybe there is some negative number we'll be reading, and we'll need to update our little helper function to do that. But for me, it's a lot easier to read when you have. Where was it? Where'd it go? Yeah, for me, it's a lot easier to read when we just say byte to int rather than this thing. It's just a lot easier to read. So yeah, that's the documentation there. So yeah, and so here's a cool, like, this is something I'm going to try to, like, when you're in these Jupyter notebooks, like, the whole point of this is you can always just press B, open up a cell, you press enter to move your cursor into that cell. You paste whatever you want to do, you hit shift enter, and you can execute code, right? And if you don't like it, you immediately, put your arrow up, you hit DD twice, and it's gone. DD is for delete. You can look at all these, as you go, you can look at these keyboard shortcuts. There's a lot of really, you can get really slick with this stuff. So, I'd always encourage you, if you think of something you want to try, open a cell, run it, and see what happens. And so this is how you can see, this is basically how we can create the same number in little and big endian, right? So this number is, I think this number is 1. I don't even know though. Oh, it's 256. So little, oh yeah, okay. So little is yeah, so this is like 1, the small byte has nothing, but the big byte has 1. So it's 2. So this is how you write the number 256, and you can see that you just like reverse the order of the bytes, and the little and big endian agree all of a sudden. So that's kind of cool, right? That's how you sort of translate between the two crazy worlds. So if you're curious, after the class, I'd say, go and play around in Jupyter Notebook and try to create some, say like, okay, I want to write the number 500 in big endian, and try to do it, and it'll be hard. You'll scratch your head, but eventually you'll do it, and you'll figure it out. So that's actually, this is let's put a to-do in here. This should have some exercises. Yeah, this first lesson doesn't really have any exercises. The second lesson has like 10 of them. So that's an improvement. Okay, so any questions on this endianness?
No.
Sounds like no. It's hopefully you kind of get it. It's confusing, and you're gonna hate it over time. It's just it's one of these, like, it's like brushing your teeth. Endianness is like brushing your teeth. You have to do it, but you don't like it. So next we have command, right? We're down to the second one, and we're trying to actually make sense of what is sent to us, right? And the whole point is, like, we want to be able to recognize a version or a virac or an inv message, right? Like when somebody sends Evo his SegWit transactions, right? Because Evo is running the newest version of Bitcoin, I'm sure. He's running 16, so he's got 0.16, so he's got SegWit, and he's waiting for these SegWit transactions, right? And so we want to know when they send us an inv message, this inv inventory message, right? Because then we're going to go request all the details and find out about our SegWit transactions. So we got to be able to recognize one of these inventory messages when we see it. And so that's why we got to read this command and make sense of it. And so, yeah, the way, I guess this is like slightly confusing. So I'm going to make one above here. So this is like what happens when we read commands. Okay, let's see if this works. So I just want to show you what happens when we read, what this looks like to begin with, because this sort of cleans it up. Okay, so there we go. So this is broken. Let me fix this real quick. Sorry. Skip bytes is equal to 0. Alex, or one of you guys actually, or maybe it was the Chandler guy who didn't, I don't think he's here. They told me about this. So this is just, don't worry about it. This is just my little helper function that you guys don't need to understand. So I need to skip. No, skip bytes onward. Okay, so. Okay, so there we go. So this is what the version. So all I'm telling it is just like, let's just skip these 4 magic bytes. So then when we receive, let's just pretend we already read those, and let's start right here. That's with the skip bytes. That's all I'm telling it. It's like, let's start here. Let's not start at the top. Let's start here. And so with our, when we're writing these functions, it just helps to be able to do that. So we don't have to throw, it just allows us to throw out 4 bytes. So this is what it looks like to begin with, right? And so I think, it would probably be better in our program, we don't want, in the future, we don't want our program to be like, okay, if message.command equals that, it's just kind of ugly, do something. We don't want our future code to look like this, because it's just like a kind of a, I think it'd be better if we just always stripped out all these empty bytes. So this is just padding, right? Because somehow, version it's a long message, right? Like this accommodates a 12-letter word because in general every letter is 1 byte, right? So VERSION, 7 bytes, right? And then this is 1 empty byte, 8, 9, 10, 11, 12, right? So it's actually, you know, I don't think there's any message that's close to that long. Let's see, what's the longest command? I guess submit order. That's 11, right? Some of these Merkle block, that's 11 letters. So some of these things actually use send headers. That's 11, right? So some of these things actually need all these 12 bytes because every letter is about a byte. There is a byte. So this is what it looks like. So what we're going to do when we read it is we're going to just strip out all of these empty XOs, right? So then our code can look like this. Then our code can look like this, right? It's just simpler, right? So let's just always, whenever we read a command, we're going to just strip out all these empty bytes. And so the reason why, you know, sometimes when you do something like this, you got to make sure that every time you read a command, it goes through the same function and it always gets stripped. You know, like if somewhere else in your code, you're doing this by itself and you forget to strip, that becomes a problem. But whenever we're touching a command, we're going to run it through this function and the bytes will always get stripped. And so that's how it goes. So let's execute this cell here, and we will see. So we made this little function like, is it a version message? All you do is you read the command and you say, you know, command is equal to version, because these are still byte strings. Is verac message, right? And this would be better. So this would be better, like, this should be an exercise. I should be having you guys go through and do this as an exercise right now, like write this function. So, sorry, I'm still figuring out how to do this class. So yeah, that's all you do is you just read the command and then, you know, check if it's right. And so, you know, this little create socket thing it was a version message, right? Right, it is a version message, the little string that we give it. So it makes sense that we have this result where, is it a version message? True. Is it a verac message? False, right? Because this string does not match the command we read. This one does. So that's how that works. And so yeah, this is really cool. Now we can recognize different types of commands, right? If someone sends us a block, we know it's a block. If someone sends a transaction, we know it's a transaction. So that's huge. We know how to differentiate different types of things, and we did a little parsing to get rid of these ugly empty bytes, so our program's a little more readable. And yeah, so now we're at the end. We basically have, as I said last time, there's 5 fields, but they really do 3 things, right? The first one is it a Bitcoin message? The second one is, what kind of message? And then the third one is like, what are the arguments to the message, or what are the parameters? And these 3 basically all serve to do that, right? Length is how much do we need to read. Payload is you read that many bytes and get it. And then checksum is like, let's just make sure that the message wasn't corrupted when it was sent over the internet, you know, because you can lose bytes and stuff like that. And so this is, I go through, you know, I'd say you can read this yourself. I go through a little bit of, you know, it's weird because TCP, the underlying thing, also does checksumming, right? So here's like a Stack Overflow thing, and this is how it kind of is in, you know, this, when you're trying to figure stuff out, right? Like Evo saw today, and you ask a question and you get like 1 answer, like 2 upvotes. And it's not like when you're doing like a JavaScript thing and there's a clear answer, it has like 5,000 upvotes. You know which one's right. Here there's only 1. You don't really know if it's right. And so the question is like, the Bitcoin messages have this checksum, right? But Bitcoin utilizes TCP, which already does already checks for lost packets, right? That's like one of the important things about TCP is it'll resend messages and it'll check every time if they've been corrupted. So at the end, you always get the correct message. And that's kind of one of the core things of why the internet works at all. And so yeah, here's this like interesting argument or, thing you can read later. He's like, yeah, I guess, Bitcoin designer Satoshi felt that this SHA-256 was better than, the checksumming that, TCP uses, which is like, we don't even know, it's funny. It's just a speculation why, we're at this like really important, why the hell does this checksum thing exist? And looking around, like this is one of the best answers I got is like, it's just a little bit better guarantee that the message wasn't corrupted in traffic. And so, it's just, check this out later. If you can find a better answer than me, go for it. What does this one say? Yeah, so basically the way checksumming works is you take a hash. Hashes, we're going to be dealing with hashes a lot, right? A hash is just a function. A hash function is a function that takes in any sort of data in one end and at the other end spits out a fixed length string, right? And for that input, it'll always give the same string. And if you even change a tiny bit of the input, the string will look totally different. And so how checksums work is for some input, you just take a hash and you just take a few characters of it. And then that basically serves as a check that, if you lose 1 byte in, sending this input to someone else, and if they do the checksum, even if they lose 1 byte, the hash will look totally different. And so the first 4 characters of the hash will also look totally different. This could use like
They're a lot easier to understand with regards to addresses because, like, you don't want to make a mistake when you write that Bitcoin address, but because it has a checksum, it makes it a lot less likely that the transaction will go through if you make a small mistake.
Great, yeah, great point. Yeah, so it's just like you're just sort of giving the computer like a thing to be like, hey, just check that I didn't screw up. It's just like it's like giving it a kind of a solution manual for whatever you did. Yeah, the checksumming is a really simple idea. It's sort of hard to explain though. So I'm going to try to improve that in the future. So yeah, I'm just going to take notes here as we go because I'm trying to improve this. Yeah, so
Ethereum addresses don't have a checksum. So if you make a small mistake with Ethereum address, you're fucked. But with Bitcoin addresses, because they have a checksum, if you make a small mistake, Ethereum, it'll likely flag up as an invalid address. Because of that checksum.
Like half the time you're sending them to like Twitter bots, right? And like, Elon Musk Twitter bots. So I don't even think it really matters with Ethereum. That's just my opinion.
It still has monetary value at this point in time.
Yeah. So whatever. So yeah, now we're on to this third thing. So we're going to try to, any questions about checksums or this stuff, or is anyone confused as hell?
Not confused as hell. I have a kind of a tangent question. Do you know of any good like resource or explainer of how a hashing function actually works and why it's trustworthy?
Yeah, I don't off the top of my head, but that's kind of what I was. Yeah, I mean, this hashing stuff is obviously it's like one of the most important things. Like Bitcoin addresses are created from hashing. Proof of work is like basically just hashing. So we're gonna deal with this over and over again. And so yeah, I'm gonna make a note of that.
I'll post the link to the video. I found a good explainer.
If you know a good one, yeah, exactly.
hash function.
Cool.
Actually.
Yeah, and I love
Yeah.
that you guys were talking about this, this question you had yesterday on this like Slack group. I think that's phenomenal. You should all do that. And if you can answer each other's questions, that's a lot better than having me answer them, because I don't know a lot of stuff. And also, yeah, like especially these kind of intro things. Yeah, that's great. So, Michael, please post that. I'd love to watch it. Cool. So, yeah, Ivo, how you doing?
Quite fine, thank you.
Making sense? Some sense?
Yes, it does.
Okay, that's good. I'm always worried that I'm just like talking into the abyss and you guys have no idea what I'm saying. And Gustavo, you following along?
Yes, I'm following. To me, it's very, very new, something new, so it's kind of getting used to it.
Okay, good.
But yeah, I'm following.
Yeah, if you have any questions, just ask them. Like I'm not going to be offended if something doesn't make sense. So, kind of stupid questions. If you have some kind of a stupid question, just ask it. And usually if you have a stupid question, someone else has the same stupid question, and it's not. It's actually a good question. So, yeah, I just gonna.
Hey, Justin.
Huh?
Oh, one more thing on the your kind of background on integers and different base systems. The Coursera Python course, I forget which one. I think it might be number 2 or number 3. Has a really good lesson or like a good like 10-minute background on all that stuff and how Python uses it. I can try and go dig up which lesson that actually is, because that could be a cool thing to
would
link
be
to.
Phenomenal. A good 10 minutes on
like different base X systems and how Python interprets them and what they kind of mean in the broader context.
Cool. Cool. Yeah, that would be great. And yeah, that's something that I like. When I learned to code, I did it with this thing called Thinkful. And Thinkful was an interesting program. It was basically like they give you this curriculum, which was just all links to tutorials on the internet. Like it was a really cool business they had. Is like they didn't actually create any content really. They just did a really good job of basically curating content that already exists, which is usually, there's so much good content out there. It is kind of stupid. Like that's one of the things as I create this course is like, I do feel kind of, it's kind of stupid to write content instead of just like going and finding the best stuff and then pointing it out. And so the interesting thing they did is, yeah, they just had links to all the best stuff of everything. And I kind of want to do that too. So yeah, if you guys ever think of, if there's something that we're going over and you're like, I saw a better resource about that than what Justin just gave us, please show it to me, and that makes my life a hell of a lot easier because I can just outsource the work, right? So yeah, let's find, Alex, if you can find that, that'd be great.
Yeah, I'll take a look.
Cool. So yeah, we're back to there you go. Look, Michael's already on it. Perfect. So here we're on to the length, the checksum, and the payload, right? Because these are kind of all three. They work together, right? And so the yeah, so there's a couple little, yeah, so let's see how we're gonna go about this, right? So let's just go down here. Well, let's start from the top. So read length, right? Pretty simple. Like read length is, this looks the same as, so look, receive of 4, bytes to int. That looks pretty familiar, right? Read magic, receive of 4, and then do bytes to int, right? It's the same function. It does exactly the same thing. Where are we? Here. So yeah, this is basically the same function as magic, and yeah, it's a little repetitive, but it's good to make your functions really clear what they're doing. So we're basically making the same function again, but just giving it a different name. And then we're reading a checksum, and this is actually like, this function is actually not exactly right. Like we should read this and interpret it as an integer. And so, yeah, this is, maybe we should just fix this. Let's just fix this as we go. And it's going to create an exception in the next thing. Yeah, so let's actually interpret it as an integer like we're supposed to, and delete this, and then return it. And so look, we have the same function 3 times now. Read 4 and interpret it as an integer. So I feel kind of stupid, but at least we understand what our code is doing, and we have these simple things. So and then here's calculate. Or so let's do that last. So then there's read payload, right? And read payload, unlike the other ones, it doesn't take 1 socket variable, it takes 2, right? Because these all have the number of bytes hard-coded, 4, or with the command it's 12. But read payload, remember, read payload's a super clever thing where we actually use a previous thing we read, the length, right? Whatever we get from here, that's what we read with read payload. So that's what it does. It just takes the first argument, we have socket, right? And then calls receive with the second argument, length. And so, yeah, read payload is really clever. And so we're going to run the code, and this is the, these 3, print length, checksum, and payload, are just going to be the results of writing, of executing read length, read checksum, and read payload. So as you see, the length 102, which makes sense, right? Because remember yesterday we saw that the message itself was 126 bytes, right? But an empty message was 126 bytes, right? And so, no, sorry, an empty message was 24, and the version message was 126. And so the length of the payload plus an empty message, which is just an empty message would just be these things, right? Right? 4 plus 4 plus 4, 16 plus, it's 12, 24. So these are 24 bytes, right? And yesterday we had all those things that were 126, and 102 plus 24 is 26. So it makes sense that that length makes sense, if we've been kind of paying attention. And then the checksum is just some integer. We don't really know what the hell this means yet. And then here's the payload, right? Here's, you got the user agent. That's the only thing we can really recognize. But the next lesson 2 is like how to make sense of this, right? And so just as like a little teaser, so you guys don't quit on me. Here's lesson 2. So what we're gonna do is, let's go to the end. The last thing we do is the last thing we do in version 2 is we send, we do the same thing we did last time, right? We, send our version message. We read the response from our peer, and then we have this new class called version message, right? And then we read what our peer told us. We read the payload, right? So here's the payload. We just read this in lesson 2. We create a class that can interpret this, and then when we print this class, this is what it looks like. Pretty cool, huh? So version, there's a number. Services, it's a nice little Python dictionary. Timestamp, this is an IP address. Here's the nonce, here's the user agent, here's the start height. So that's this and this table are the same exact thing. We just don't know how to interpret it yet. And so that's lesson 2, is like, how do you turn this into a pretty little table where we know all the data. So that's what we'll do next time. And so, this should make sense. These are the 3 values, but then we have this check something. What the hell? How do we go about this? So we need So I just corrected this. So this should be 2. No, we need int.2 bytes. Let me see, do we? I think int.2 bytes is little live coding here. Sorry. Well, here, let's just go back. So that's what it'll look like. I'm just going to go back and undo this little change of fixing the fix me. And so you'll understand it better. So this is how, when we read the checksum, right, we get, now we get some bytes, and this is wrong. We should interpret this as an integer. But what we can do now is this function, when we call this function on the payload, somehow magically it produces these bytes, right? And this is a checksum. What you do is you go and you call SHA-256 hashing algorithm on this, or on this whole payload, right? And then you get we're gonna make this a little more clear. So okay, let's execute it again. So if we go look down here, so this is what, sorry. So if we go down here, we see after the first round, so when we're calculating the checksum, we run it through this thing and we take a hash, right? And let's print the hash. This is what it looks like after one round, after we do it once. But the way the checksumming that Satoshi uses, he does SHA-256 twice. I'm not exactly sure why he does it twice. Someone explained it to me once, but I forgot. And so we do it again, and here's the second time, right? And if you look at it, if you look at the first 4 bytes, or first, I guess that's 4 bytes? I thought it was supposed to be, yeah, I guess they're the first 4 bytes. But if you look at it, like, what the hell, that is exactly this, right? So and this checksum came directly from the message itself, and here we reproduced it. And so the last thing of this code is it just takes the first 4 bytes and returns them. And so this is this little routine here, checking this is what we do every time we get a message. We're going to check the checksum to see if it was corrupted or not. And so hopefully that kind of made sense. A little live coding there was, and it's not completely right. What we should do is we should interpret this as an integer, and then when we run it through here, I guess at the last step here, we should, if we want to be completely correct, bring it into the right, we could turn it into an integer in both these places. But it's really not that, like, this works. We're just doing it in the raw bytes instead of doing the comparison in integers. So yeah, does that make sense? That was sort of a bad explanation, but does that make sense at all? Any questions?
Well, hey, sorry. Where does the original that original checksum come from?
This one here.
Yeah.
Yeah. So this is just we just called read checksum on the socket. So we're just getting it straight from the message. So like in real life, so yeah, in our function, we're almost at the end. So when we have this class, so yeah, this is the last thing we're gonna do, right? Network magic is wrong. What the hell? Well, that is probably, I wonder if I messed it up. Skip bytes, is that? Let me see here, print magic. Oh, okay. So we have, so here we have a dead peer. We're trying to read the magic and we get 0 bytes. The number is 0. And so that just means when we called read magic, they sent us an empty string, which means they're not, like, they hung up on us. So we're going to need to find, I think we found a new peer yesterday, didn't we? Or I guess I deleted that.
Which one did we DOS?
Maybe it was this guy. I don't know. So yeah, this is something you'll encounter every once in a while when you're debugging something. It's like, just make sure that the guy on the other side hasn't hung up on you, like this guy did. So Boardman, I wonder where Boardman is. Like, there's a lot of them named Boardman. Look at these. Look at all these Boardmans.
Well, that's the location.
Yeah, but that's a lot of the same location, isn't it?
Maybe it's where, like, I don't know.
Wow, look at that. They're all Amazon Inc. They're all. Oh, so this is probably an AWS data center.
Oh yeah.
Yeah, look at that. And so here's DigitalOcean. Right, so Frankfurt, there will be a bunch of Frankfurts in North Bergen, right? So like Frankfurt, all DigitalOcean. See that? All DigitalOcean. And then Bergen. Like there's a few of them, all DigitalOcean. So that's interesting. A lot of these full nodes are running on data centers and cloud providers. That's cool. Let's learn something new. So let's go down to the end here. Alex, I'm still answering your question, okay? I haven't forgot about you.
No problem.
So, okay, well. Okay, so now it works. Now we actually get the right number because we found a peer that isn't dead. So that's good. Let's just, for the sake of next class, let's. Actually, let's just delete those because you're supposed to fill those out yourself. Okay, cool. So this is the last thing we're doing here in this class is we go and we still don't know how to write one of these versions to create one of our own. So I'm still giving you this one that is already set up, but we know how to read them now, or we know how to like read the parts of them, the outside parts. So what we're going to do is we're going to we just do this. We take the socket and we just read. We have this class method, it's called. So it's just like a method that you can call on the class itself. Like this isn't a, most methods are like this, right? You call it on the instance, right? There's not an example, but like when we saw int, right? We, or like, actually this was a good one. Here's like instance methods are usually like this, right? You have bytes and then you do instance.replace, right? That's usually how it works. But this is different. This is a so-called class method. So you don't call it on the instance, you call it from the class. And the way it works is when you call it, the first thing is basically like is like this, the class itself. And so what you do is at the end, you basically go and create a version of the class, right? And so so message.fromBytes is this magical function that takes in a socket, and it'll give you an instance of this message class. And that's basically the same way it works. That's the same way this works, right? So int is a class, right? And int.fromBytes takes in bytes and then this byte order, and then it actually gives you a number. It gives you an instance of the integer class. And so this is actually the same thing that we're going to do down here. We're just going to make this class method that can take a socket, read from it, and then create an instance of this message class. And then so, to answer your question, Alex, in the wild, this is where the checksum comes from. It goes down these attributes, magic. It reads magic, right? And it checks, is magic equal to the magic that this magic we took note of earlier? If it isn't, let's raise an error. Let's say you fucked up, this is the wrong network magic, right? And then it goes to the next one, command, reads the command. Then it goes to payload length, reads the length. Then it goes, reads the checksum. And here it is. So this is the answer, Alex. We're just reading it straight out of, every time we read a message, this is the fourth field we encounter is the checksum. And so that's, when we do this, well, here, let's just keep looking. So we get the checksum, right? And then we get the payload with our read payload function. And then let's just do two other checks before we finish here. Let's do two checks. First, let's go and calculate, let's make our own calculation of the checksum, right? This is the calculate checksum function that we wrote, which is just called SHA-256 twice on the payload bytes. And let's do a comparison, right? If calculated checksum is not equal to checksum, let's raise an error. And I'll just show you, there's an easy way to, when we call this down here, we don't get any errors. It works, right? But I'll just show you, this is actually doing something. If we add, the byte string 1 to this and call it, boom, checksums don't match, right? So just imagine if the payload somehow got a 1 appended to it, a byte 1, all of a sudden our checking code here is like, boom, something happened to this message. It's not the message we were sent. Let's raise an error. So that's pretty cool. It can, if this payload is tampered with in any way, it can detect it. And then finally, it sends this payload length message. And so this, remember last time where we were getting two messages together. We were getting the version and the verac messages at the same time. This would actually catch that. The payload length would be like 102, right? That's what we saw. But if there were actually no, this wouldn't catch that, actually. This only catches, yeah, this would only catch if the payload wasn't long enough. So yeah, maybe, that's a little confusing. I probably shouldn't even have this in there. We can do that later when we get more sophisticated. But yeah, so this is how, we don't need this either. This is how that works. So does that make sense, Alex?
Yeah, we're basically just verifying that the checksum that they gave us is two SHA-256 hashes of the payload?
Yep, exactly.
Okay.
So perfect. The checksum, as Alex said, the checksum is SHA-256 twice of the payload. That is important to remember. And
it doesn't check the whole hash though, right? It just checks a portion of the hash.
First 4, yeah.
Yeah.
Yeah. Oh, good point. Yeah. So as Michael said, the checksum is the first 4 digits of the SHA-256 twice of the payload. There we go. Now I think we're actually correct. Thank you, Michael.
So
cool.
it's still, there's a tiny probability that the checksum matches, but you've got the wrong payload.
Yeah. So yeah, exactly. It'd be 16 to the fourth, right? Which we just saw was like 4,096 or something.
But because that's so tiny, generally the checksum does what you want it to.
It's bigger than that. That was 16 to the third. So yeah, so 1 in 65,000 is the probability that you'd have a match. So yeah, 1 in 65,000 bad messages would match the checksum. So yeah, it's not perfect. And yeah, TCP does checksumming too. So I don't understand any of this. You know, somewhere. Okay, so here you go. So here's the, you know, this is a TCP message, which Bitcoin is built on top of. This is, that's what it looks like. So here you go. So Eric, the TCP checksum is considered weak by modern layers, by modern standards. Data link layers. So I bet you'd call Bitcoin would be a data link layer. Data link layers with high bit error rates. And so maybe, you know, the Bitcoin network has to go across the Great Firewall of China, right? So that's probably a pretty high bit error rate. May require additional link error correction detection capabilities, right? So this right here might be why, I bet this is why we do this SHA-256. I bet this is basically why, you know, why we have this extra checksum is that the TCP checksum is kind of wimpy. So yeah, there you go. I mean, I'm not totally sure myself, but it's, you know, it's starting to make some sense. So yeah, that's the end of this lesson. Any questions?
Yeah, I have one and then 2 stupid questions. But
yeah,
someone else
good.
can...
So three stupid questions?
Huh?
So 3 stupid questions?
Okay, fine.
Sorry. Go for it.
Does someone else want to go first? Because I'm talking all the time.
No, we like your beautiful British accent.
Okay, thank you very much. So the slightly less stupid question is just referring to when you're saying, why is it hashed twice?
Yeah.
So when you're going between a Bitcoin public address, a Bitcoin public key and a Bitcoin address, you use 2 hashes of SHA-256 and then RIPE-MD. Yeah. And the reason behind that is just in case there was a supercomputer that could brute force SHA-256, it's better to have layers of redundancy. So you'd have to brute force SHA-256 twice, and you'd have to brute force the different hash function RIPE-MD to be able to get back to the public key from the address. Yeah. So I can see why you'd want like layers of redundancy when it's addresses and public keys and private keys and things. But I don't understand why you'd want those layers of redundancy here. It doesn't seem that important. Yeah. Why would someone want to brute force this particular hash function?
Yeah, I don't know. I mean, maybe like if you had an attacker, you know, I mean, maybe if they had some clever way to like, you know, if you could make the probability much less, you know, if you could produce, well, I don't know. Yeah, maybe I don't know. You know, maybe if you had,
it doesn't seem that important. You know what I mean?
Huh?
It doesn't seem that important to add another layer of redundancy.
And this is one of those things that's so interesting about, you know, learning these like very, I mean, this is like the really kind of, like we're going to be continuing to do this really low level stuff. And the interesting thing is like, you know, you always think of like, what was it like when this was designed? And I kind of think the answer was like, you know, this Satoshi guy or girl or whatever, a couple people, you know, it wasn't more than a few people at most, you know, they're just like, these like weirdos sitting down in a basement, you know, and maybe he just was lazy and, you know, already had the SHA-256 twice hash function. He just, just sticks it in again. You don't know.
You couldn't be bothered to delete it.
Yeah. He's just like, it was just, maybe the answer is just he was lazy, Like, I'm sure that's the answer with some of this stuff, like having the byte order backwards sometimes, or like there are clear, I mean, when I took Jimmy Song's class, like he gave a couple of examples of stuff where there was like off by one errors, and I forget what they were, but it was just clearly like Satoshi didn't test his code, like what the hell, man? It's just sort of funny.
I think it's check multisig. Or something to do with multisig, you have to put just a random 0 in.
Yeah, exactly. Yeah, so there's just like I think there might be more than one off by one error that was introduced by Satoshi's laziness.
Okay, now the two stupid questions.
Yeah.
So with this version, and you've got like /x's, /x's. Why do you need all of those x's? Why can't you just say at the start hexadecimal?
So yeah, so this is a good question. I think that these x's are just a Python thing. Like I think that the way that's a great question. I thought the same thing. So like the way it's sent, remember this is like sent over the wire as this, right? And they're not even spaces here. They put the spaces here to make it to make it a little easier to see byte by byte what's going on. But it's just 0 to 9, A through F, digits. That's all it is. And so these X's are just made. This is just the Python thing to make it a little. It's like delimiters when you work with it. So you're not just. I mean, this would be a lot harder to understand if there weren't the delimiters. So you could tell what is a byte and what isn't. It's just a way to make it a little more. I mean, I think it's the same thing as this. Like, So Python has this, right? When you deal with when you deal with numbers, you can specify the commas, like we do you can do it this way. It just makes it a little easier to read, And so I think that's basically what these \x's are, but that's a good question. Like, what exactly are the \x's? That's how I understand it. I'll research that a little more.
Okay, and then final question is, and maybe it's the same answer. Why are they split into pairs?
Pairs. So so each one of these. So a bit is 8 byte, or a byte is 8 bits, right? And so so we need no. So each one of these is, how do you say this? So like, just a second.
So I mean, I understand hexadecimal, and I understand that like F9 is basically 9 times 16 to the power 0 plus whatever F is, 15 times 16 to the power 1.
Yeah.
But then why can't you just have a really long hex number? Why do you need to split it into pairs?
That's a good question. I don't know exactly why that is. I mean, this could be.
Is it just ease of like making it easier to read?
I don't know. I mean, it is when you go and look at like this in particular, how why do you do it by pairs? I mean, I guess it's because you just like when they were doing this, they could have done it with like, instead of these two. I mean, I bet the reason why is like the first versions of the internet, they were sending ASCII, right? And ASCII is like 1 through 128 or so character. You know, each thing is 1 through 128, and like then there's some other stuff as far as I think that's how ASCII is. And so that's what they were sending, and so they wanted each thing to be, they wanted like each unit to like represent one character, I bet. And so this was like the right size to send one letter over the internet. That's what my guess is. Because this would be 16, this would be, you know, these two characters is 16 squared, and then so that's 256. And so you could fit 128 into one of these. And you could probably, I don't know what they did with the rest of the characters, but so extended ASCII. So yeah, here's what the extended ASCII was. So like, you know, this is, that's my guess. I don't know. That's another good question.
Okay, thanks.
Yeah, I'm not sure. Yeah, I mean, I think it's just arbitrary. It's just like that's the unit we wanted, I guess. You know, who knows? I'll look into that. I mean, but I think it's pretty sure it's a TCP thing. Like this is just like we're just using what TCP gives us, right? Because the way the TCP is, or actually it's not. It's an IP thing, Internet Protocol thing. Like the Internet Protocol is the thing below TCP. It's just how do you send bytes between addresses, right? And this is the thing that was like, you know, built in the 70s and 80s. And so I think it's actually an Internet Protocol decision. So that's where we should look for this answer. Yeah, so it's a good question though. I'm not sure. Any other questions? That looks like a no. Well, go ahead.
In hexadecimal, each of the characters represents one thing. Was it so? So, for example, F is one separate thing, the 9 is separate thing. I mean, I'll probably go to the wiki to read about it, but nonetheless, I just wanted to ask.
Say that one more time. Just repeat your question.
So, one of the questions that Michael asked was about pairs, right?
Yeah.
So pairs in the sense that we have F9, B, B4, and so on and so forth. Mm-hmm. So basically this thing is 1 byte, right?
Yeah.
And how is it that you're reading it? For example, a minute ago you said that B4 was something like 16 to the power of 2 or something. I couldn't quite understand that.
I can give this a go, Justin, and then if I do a bad job...
Yeah, go for it.
So, like a normal number, if you say like 365, 365 is the equivalent of saying 5 times 10 to the power 0 plus 6 times 10 to the power 1 plus 3 times 10 to the power 2. Does that make sense?
Yes, it does.
So like that's like base 10. And like we're familiar with base 10, like we use base 10 numbers all the time. But with hexadecimal, it uses base 16. So it uses 0 to 9, and then A is 10, B is 11, C is 12, D is 13, etc., up to 15. And so then how you read hexadecimal is exactly the same as what I was saying with base 10, but with base 16 instead.
Oh,
so
right.
like the digit at the end on the left is times 16 to the power 0. The digit to the left of that is times 16 to the power 1. The digit to the left of that is times 16 to the power 2. Exactly the same as base 10, just substituting 16 with those powers. Does that make sense?
Yes, it does. So, for example, we have 4 times 16 to the power of 1, and then I'm just reading the version message right now. So, or let's say the very beginning where we have the F9. So we have F times 16 to the power of 1 and so on. Is that how we read it?
So where are you saying? F9, right? So F9 is 9 times 16 to the power 0, which is basically just 9.
All right.
And 15 times 16 to the power 1.
Okay, now it makes perfect sense.
Whatever 15 times 16 is. What is it? 160. 240 maybe?
Oh, you have to check. 15, yeah, 240, exactly.
So you just do the same, you do the same thing as with base 10. It's just we're familiar with base 10, so you don't have to think about it because we're using base 10 numbers all the time. With base 16, you actually have to do the calculation yourself with each of those digits.
Yes, it makes sense. Thank you.
No problem.
Yeah, this one here is kind of a good, Ivo, I'd recommend you go and look in the hexadecimal section. Like, look at this example, and then go and make your own versions of this with small numbers, right? So it's good to start with binary. So here's 2 to the power 0 is 1, right? So you're gonna have 1, and then 2 to the power of 1 is 0, none of those. 2 to the power of 2 is 4, none of those. 2 to the power 3, 8, none of those. 2 to the power 4, 16, one of those, right? And so that makes sense. It's 1 plus 16 is 17, right?
Yeah.
And then with octal, you do the same thing. With hexadecimal, you do the same thing. It's really simple to look in hexadecimal, right? It's 1, 1, and 1, 16. That's 17. Octal's pretty simple too. It's 1, 1, and 2 8s. So I'd say just play around with some of these and just try to make it, try to make the different bases match with small numbers, and then go to a really big number and see if you can, predict what the, try to predict what this will output, So this is a good thing to kind of play around with. And this, I think I should probably have an exercise here, a couple exercises here. Yeah, I should, yeah, you really have to play around with this. It's not really intuitive. Yeah, any more questions? That was a good question, Ivo.
Thank you.
Alex, you hanging in there?
Yeah, I am. I'm gonna go back and actually do this at some point.
Cool.
Myself.
Nice. And Gustavo is Gustavo still with us?
Yeah, I am here, but I'm still learning, so to me, everything is very new. I'm still catching on.
Cool. Any questions?
No.
No questions. Cool. Great. Well, I think that's the extent of it. We've been at it for an hour and 20, hour and 30 minutes. So let's call it a day, and maybe we'll figure out when. When would you guys want to do the second lesson? Would you want to? We could do it next weekend. We could do it sometime. I think it's a lot easier to get people to show up on the weekend.
Yeah, I agree too. The weekend it's easier, at least for me.
Yeah.
Yeah, weekend works for me too.
Okay, well maybe we'll try to do the second lesson next weekend. Maybe we could see if we can get one of them done. We'll see. Maybe we just do one lesson at a time. We'll see. But yeah, let's shoot for next Saturday, kind of similar times, and a couple of the people who kind of fell behind, I think we'll be able to catch up. They've been off. One of the guys is on tour right now with his heavy metal band, which is kind of
cool.
cool.
God. I saw he said tour. I thought he just meant traveling.
Yeah, no, I think he's this huge guy with all these tattoos, and he looks really intimidating, but then he's the nicest guy you ever met. It's pretty cool. So yeah, that's it. So I guess let's see you guys on Slack. Keep posting these cool things, and I'll talk to you soon.
Is there any homework to do for next week? Oh, sorry. Go for
homework. Not really. I got to get better at assigning home. I'll get back to you. I should. yeah, because it's. I'll think about it. I should try to. Let me write that in our little thing. This is becoming more than one thing.
And I interrupted Alex. What were you going to say, Alex?
Oh, no problem. I was just going to say, Justin, I'm going to be in Austin on August 16th and 17th. So I don't know if the meetup is going to meet during that week, but if it met on Thursday, I could actually make it in person, which would be cool.
That would be cool. Yeah, no, I'm trying to organize that. We haven't. Yeah, that's the day it would be. So they haven't gotten back to me whether I can reserve it. Like, I'm trying to book every other week, and I don't think they really. That's a lot. But I got so that you remember that kind of older guy that showed up. He's really quite sophisticated. He is going to present one of his projects, and then another guy is going to present something that he's kind of been exploring. So finally, it's not going to just be me. And Michael, I will post the video of our second meetup today. I will do that.
Yeah.
Yeah. How do you do that on YouTube? I gotta fucking do this. Okay. Well, I'm gonna go try to upload this crappy video to YouTube, and I'll think about homework and talk later if there are no more questions.
Cool. Cheers,
Awesome.
Justin. Cheers,
Yeah.
guys.
Thanks. Good
Bye,
talk,
guys.
guys. See ya.
Bye, guys.